Hello everyone, I'm Joshua Bruton. Today I'm going to be presenting a work that's been accepted for publication at the International Conference on Image Processing 2022. The work is a 5-page conference paper that I completed towards completion of my Master of Science in Computer Science at the University of the Witwatersrand, which was finished earlier this year. The work is entitled Translated Skip Connections, Expanding the Receptive Fields of Fully Convolutional Neural Networks. As the title suggests, receptive fields are quite an important concept here. I'll just explain them briefly. You can imagine in this diagram, if we have this red neuron at the bottom here, the proportion of the image that is inputted to the network that it can perceive is what we call the effective receptive field. So in this case, the neuron is seeing this 5x5 portion of the original image. You can imagine as we move back through the network, or if the network were larger than just these two layers, then it would see a larger and larger portion of it. This notion is very important in computer vision and image processing because you can imagine some problems are directly tied to this limitation in networks. For example, in a medical imaging context, perhaps where we're telling the difference between left and right lungs, if the portion of our network can only see this receptive field where the white square is, you can imagine it can't really make an informed decision about whether or not it's looking at the left or right lung. Obviously, surrounding neurons can make that decision, but these pixels in the center may never actually be perceived by a neuron that can tell with enough information whether or not we're looking at a left or right lung. Likewise, in like telling the difference between lanes, you can imagine a few different concepts where this would come up. Also, if there's ever any sort of correlated classes, then it could have some issues. So if there are two classes being next to each other has, for example, like horse and rider, or like desk and keyboard, these sort of correlated classes, increasing receptive fields can often help quite a lot in telling object labels. So there's a number of different ways that we can expand receptive fields. Often it's just done implicitly by using deeper networks or larger convolutional kernels. Obviously, these have the primary limitation of increasing the number of parameters. If instead of using 3x3, we used 5x5, sure, we've got an effective receptive field that's larger, but we've also almost tripled the number of parameters we're using, Deeper networks have a similar problem where if the only problem we need to solve to solve whatever domain we're applying our network to is increasing the effective receptive field, using a deeper network isn't necessarily the most efficient way to do that. Smaller images is another way. This can lead to information loss, but if we just downsample the image, you are going to see a larger proportion of it, even if your receptive field size hasn't actually changed. Pooling is another thing that increases the effective receptive field, but it is not a learnable approach. So it has those fixed parameters. And obviously, you would prefer to use some kind of learnable approach. Strided convolution can also work, sort of similarly to pooling in a sense. Dilated convolution is another approach. And dilated convolution really stands apart from these other 5 because it's designed specifically with increasing the effective receptive field size in mind, and it does so without increasing the number of parameters. So what is dilated convolution? You can imagine if we have this 3x3 kernel over here, this has a dilation rate of 0. Most networks we use do. But if we expand, or if we dilate rather, this kernel in the following way, by creating these gaps between each of the pixels in the kernel, then we've expanded the proportion of the image that we're looking at. And you can imagine we can dilate the kernel arbitrarily much. The only problem is that we're creating these gaps, which could potentially create some information loss, or maybe lose out on the correlation between the neighboring pixels. You can imagine there could be some loss in doing this, and indeed there is often. But dilated convolution has been shown to improve performance over normal convolution in quite a few different domains. So our approach sort of improves on dilated convolution and outperforms it in some cases. It combines two different concepts. One is the concept of a skip connection, which, if you're familiar with CNNs, you're undoubtedly familiar with. The other is the concept of the translation function. So we sort of combine these two notions to get a translated skip connection. And this is a novel neural network module that we're proposing that you can really embed into any FCN or CNN. Exactly like whenever you can use a skip connection, you could also use a translated skip connection. So how do these two things, translation functions and skip connections, work? The translation function is really just a notational thing. You know, how you implement it isn't too serious, but you can imagine if we have this input image X, we define this translation function where we can translate X, the original image, left by a half, or up by a half, or diagonal by a half. And we could really change this to any factor, just we're using half for the sake of example. So if we translate the image a half left, the portion of the image that goes out on the left comes back in on the right. And then likewise for up and diagonal. And you can imagine diagonal when you're implementing it is just up and left, or you know, down and right, however you're using it. Why this is so important is because you can imagine if we fixed a 3x3 convolutional kernel in the middle of the image, as we translate the image around, that kernel is seeing a larger and larger portion of the image. And you can probably see where this is going just from that. The other sort of concept that we use is skip connection. I won't spend too much time on this, but we've got this input X. It's fed into the layer to give us f of X, fed into the next layer, which would give us g of f of X. But what we also do is we take this original input X, we pass it right around the network, and we add it or concatenate it onto f of X, and we feed that into the layer to get g of f of X plus X, or g of f of X concatenated with X. So this creates a number of improvements in convergence. It also allows us to zero weight layers if they aren't contributing at all to our classification. So this produces a number of improvements over not having skip connections, which is why they're a sort of mainstay in all networks at the moment. So we essentially extend this concept of the skip connection with the translation function. So instead of having g of f of X plus X, or g of f of X concatenated with X, we use this as our skip connection. So it sort of combines both types of skip connections, additive and concatenative. And that decision isn't as arbitrary as it is sometimes. Usually it's just an implementation detail, like do you want to use additive or concatenative? But we decided with some intention on which ones we wanted to use. So we've got one additive skip connection and three concatenative ones, and also the input is translated. The skipped input is translated, and that gives us a translated skip connection. So the skip is represented by this equation. We get g of f of X plus X, so that's just a normal skip connection, and then we concatenate on the skipped input translated by some factor, left, up, and diagonally. So this factor, this L here at the top of the factor, represents the layer that we are in the decoder of the network. And look, if you don't have a decoder, you could translate by some fixed factor depending on the depth that you are in the network. Because we're using an FCN, we use the layer we are in the decoder. So you can imagine as we move up the decoder, we're going translating 1/6, then translating 2/6, then 3/6, then 4/6, seeing gradually a larger and larger portion of the image, or moving the kernel further and further away from where it originally was. So why did we make this choice to use additive and concatenative? So there's the additive skip connection. This is essentially serving the purpose of a normal skip connection, right? Normal skip connections are still very important, and you do well not to just take them away. So this is just the unskipped inputs being added exactly like it would be normally. Then we have these concatenative skip connections. The reason we chose to use concatenative skip connections for these is because if you're seeing a portion of the image that you don't need to see, or that the network doesn't need to see, it can just zero weight them, because by concatenating it, it must have its own, it will have its own weights. So then we've got so the one issue with this is that as we translate over the image, as I mentioned, we're seeing portions of the image that this kernel wouldn't usually see, and it doesn't really know where those portions come from unless it's told more explicitly. So we use something that we've called optional translational equivariance. I think it's also been called or coordinate convolution. But this is just the name we gave it here because it's pretty appropriate for what it's doing. So essentially, if we have RGB, this is a sort of normal pixel. It has like a red, green, and blue channel. Instead of that, we have five channels for each pixel. So red, green, blue, and then its normalized x coordinates and its normalized y coordinates. So basically, the percentage of it is in the width of the image, and the percentage it is in the height of the image. So this essentially means that every single pixel is encoding its position in the image. So when we translate over the image, whichever kernel you're getting input, you always know, or the network always knows where it came from. Cool. So this is the network, the architecture that we propose and test. You can see it's exactly like a normal fully convolutional neural network. The only difference is that these skip connections shown here in yellow are now translated skip connections. So as we move up through the image, as I said, so here at the bottom, it would be translated 1/6, 2/6, 3/6, 4/6, 5/6. And so as the image is passed up through the network, the skipped input is passed up through the network, we see a larger and larger portion of it in the kernel. This essentially means that by the end of the network, the kernel, each kernel has seen, or it can weight the entire image. It's seen basically the entire image. So the receptive field can cover the entire image, and you can imagine each layer we add, that translation function is going to see, even larger proportions. So even like in high res images, you would be able to expand the receptive field to see the entire image. So in order to test this, we tested on real world use cases later. But in order to test this first, we start with an ablation study of translated skip connections and optional translational equivariance. And we do this ablation study on a synthetic data set. And this is sort of how the synthetic data set is structured. We have every single permutation of top and bottom and left and right of multiple different colors. And essentially, you just have to tell the left of the image from the right of the image, or the top of the image from the bottom of the image, depending on how the bisecting line is shaped. You can see it's a super simple problem, right? But a lot of fully convolutional neural networks, actually, this problem is impossible for a lot of them because their receptive field just isn't large enough. And sure, you can use like dilated convolution with like a dilation rate of 5 or whatever, but you're then just skipping large portions of the image, and then some of the kernels produce a lot of artifacts, particularly around the line. So you can sort of picture what's occurring, especially when the kernel is at the top of images like this. There's no way it can tell whether it's at the top or the bottom of the image, right? And it also can't tell whether the bisecting line is horizontal or vertical. So it doesn't know whether it should be labeling top or left or right, or it doesn't know what it should be labeling at all. So you can see that the effective receptive field sort of defines your success in this problem. So testing on this problem, we test every single combination of translated skip connections and OTE. So this bottom green line is when we apply UNet without optional translational equivariance to the data sets. And you can see it's just impossible, as we sort of would expect. If we apply UNet with optional translational equivariance, then it can at least know whether it's on the left or right or top or bottom of the image because it's given the coordinates. But it can't know whether the bisecting line is left or right. So it improves performance, but not greatly. So that's with optional translational equivariance. Then we apply translated skip connections without optional translational equivariance. And you can see it gets, much better performance. And then finally, we apply translated skip connections with optional translational equivariance, and then we finally get perfect performance, which is what you would want from a problem this simple, you know. So interestingly, with translated skip connections without OTE, you can see the variance around here is quite high. We theorize that this is because the information provided by translated skip connections are very complex, because it's being translated around the image, and without optional translational equivariance, the network has no idea where its inputs are actually coming from in the image. So it takes a while to converge, and when it does converge, it converges at a lower accuracy. So, you know, this result shows that translated skip connections and OTE don't just improve performance; they're also quite complementary, as you would expect them to be. So next, we test on a bunch of real-world data sets. So we test on a COVID-19 data set, the INRIA image labeling data set, Land Cover AI, Carla, and VOC2012. And you can see TSCnet outperforms or matches its nearest competitor in pretty much every single case. In every single case. It also has lower variance in a few cases. So that's also good. The only cases where it's matched is with Carla on BNet and VOC2012 on by the dilation 3 model. So that is a UNet with a dilation rate of 3. Sort of makes sense, and we explain why we theorize that to be the case in the paper, in the discussion of the paper. So if you would like to see the full dissertation or the paper, it'll be linked somewhere. I don't know where you're watching this. Could be on the ICIP website, maybe my YouTube channel. Yeah, if you want to see the full dissertation, you can just reach out to me. It also might be released on archive, but yeah, just check the description. Yeah, thank you for listening. If you have any questions, feel free to ask.